Okay, now let's look at how these features are used inside a classifier, and in particular I want to introduce the notion of linear classifiers. Our feature-based maxent classifiers are linear classifiers, and so what that means is that at the end of the day what they're going to do is going to have a set of features, and then it's going to calculate a linear function of those features, which will end up as a score for a particular class. And the way that we do that is that for each feature fi, we assign it a weight lambda I. And so what we're going to do is then consider for an observed datum every particular class that we can give it, and then we're going to work out what features match against that datum, and therefore what the weight of the votes for a class are in terms of these lambda I weights. So let's look through a concrete example. So this is again the example for where we're going to be wanting to determine a class for this word, where our choices here are person, location, or drug. And so what we're going to do is consider which of the classes gets the most votes in terms of the three features that we defined before. So the vote for a class is just going to be the sums of the weights that are assigned to each of the features. So if you remember the three features from before, the first feature looked whether the preceding word was in, whether the word is capitalized, and then whether the class is location. So it's not going to match here, but it is going to match over here. And so that's a feature that would tend to pick out locations, so we'll assume that it has a positive weight of 1.8. The second feature was then also a feature that matched on locations, and it looked for an accented Latin character here. So it will match against this datum, but not against the other two datums again. And so in general, I'm assuming that that feature, at least for American English, will have a negative weight because you're more likely to see accents and things like person names. So it might have a weight of minus 0.6. Okay, then the third feature that we had defined was that the class was drug and the word ends in C. So of these three datums, the one which will match is this one here. And it's not true in this case, but in general, I think that's likely to be true because quite a few drug names like Zantac end in a C, whereas not that many regular words do. So maybe we'll give that a weak positive vote and say that that feature has 0.3. And so then what we're going to be doing is that we're going to be choosing the class that has the highest total votes. And so there are three class choices here. So this class choice of person actually matched no features, so its total vote is 0, which is a kind of neither a positive nor a negative preference. This class choice of location in aggregate had a vote for it of 1.2, and this class choice of drug in aggregate had a vote for it of 0.3. And so what we're going to choose as the class which maximizes this voting quantity is going to be location. There are many ways to choose the weights for the features in our classifier. So for example, perceptron algorithms, what they do is they look for a currently misclassified example and then they nudge the weights in a direction that will correct the classification of that one example. Another popular form of discriminative classifier is support vector machines, which we're not going to cover in these classes, but what they're trying to do is create a lot of distance between examples of different classes by adjusting the feature weights to achieve that direction, so they're called max margin classifiers. But the classifiers that we're going to look at here are maxent classifiers, which are in a family which is referred to as exponential or log linear classifiers. In general, this family has lots and lots of names, so things in this class are also referred to as logistic classifiers and Gibbs models, which are very closely related to maxent models. And so the idea of this class is that what we're going to do is we're going to make a probabilistic model out of the linear combination that we already saw, the sum over the dot product. So as a dot product, the lambda f dot product, which is the sum of lambda ifi of c and d. So how do we do it? Well, what we're going to imagine doing it is kind of in the simplest possible way. So here's this sum of lambda I fi of, which is a function of c and d. Now the problem with this linear combination is that it might come out as either positive or negative, and that's bad if you're a probability. And so what we're going to want to do is we're going to make that always positive, and the way we're going to do that is taking an exponential of it. So we're going to take e to this power. So this is something that will always make the vote positive. And this form I'm showing here, so it's e, that's, you know, the 2.818, etc. And then you're raising the feature dot product to that. So you can also see it just written as e to the lambda dot f, where these are our vectors of features. Okay, so now we've got something that's a positive quantity, but it's not necessarily a probability. So we're going to make it a probability in the simplest way possible too, which is we're going to normalize it. So this is some kind of score for one class, and so then what we can do is work out the score for every class and divide through by it. Okay, and then we're going to say that this quantity here is the probability that we assign to a class, probability of a particular class for a datum given a certain set of parameters, where this is our vector of all the parameters. And so we can work out a concrete example, so that for our previous example where we had the probability of choosing location given in Quebec, well, what we're going to work out is for our numerator, we've got the features that match, so we're working out e to the 1.8 plus minus 0.6, and then we're going to divide that through by the total votes for all of the classes. So one class had no features matching, the second class had the single vote of 0.3, and then here's the one for location, which is e to the 1.8 plus minus 0.6. And you can work that out on your calculator, and it comes out to be equal to about 0.59. And so these kind of terms there, you can also simplify them. So adding exponents is just the same as multiplying. So you can also think of this as e to the 1.8 times e to the minus 0.6. And so that's the sense in which each of these features gives an extra multiplicative term that changes the probability. That when you add a feature, you're adding an extra multiplicative term that changes the probability. So if you work through all of the examples of the different classes, I'll just skip and show the math, that what you get is that these are the different probabilities. And so note that we're giving a probability of each of our three class choices, and together that they do add up to 1, and that's precisely by the normalization that we've defined here. So these weights lambda are now the parameters of a probability distribution, and we're combining them by this function here. This function is also referred to as the softmax function, and the reason for that is because when you're using this exponent function to make things positive, things get bigger. So if you take something like e to the 3, that's approximately 25 or something. And so the effect of that is the features with the strongest votes dominate more strongly in this form here, and so it's sort of like a soft maximum, so it'll give you a value that's most strongly determined by the biggest votes. So in Maxent or exponential models, what we're wanting to do is say, given this model form, what we're going to do is try and choose parameters lambda I that maximize the conditional likelihood of the data according to this model. So we've defined probabilities over data and classes, and we're going to maximize the choice of classes according to that probability distribution. So a feature of these models is that we construct not only a classification function, but also a probability distribution over classifications. So there are many good ways of discriminating classes, so SVMs, boosting, perceptrons, many machine learning algorithms will give you a way to distinguish between classes, but these other ones aren't as naturally and inherently thought of as distributions over classes, though people have thought of ways to extend them in this direction. You may have seen logistic regression or multi-class logistic regression in a statistics or a machine learning model. So that maybe divides people. If you haven't seen these before, don't worry about it, because the presentation and derivations that we show here are completely self-contained. But on the other hand, if you have seen these models before, that something you might want to do is just think about how what is presented here is a little bit different. And it's effectively different in two ways. One is the choice of parameterization. So the parameterization is slightly different than the parameterization that's normally shown for multi-class logistic regression models in statistics. And there are kind of pluses and minuses to the presentation here. The minus is it's slightly statistically inelegant because the model is over-parameterized. But the plus is that this style of parameterization is actually very advantageous to NLP models, which have the property that there are always a very large number of features, most of which are inactive for any particular datum. But secondly, the thing to observe is that the way things are formulated here is in terms of feature functions of both the observed data and of the class. This both shows how you can put text into the model most simply, but it's actually also a more general formulation than you normally see for multi-class logistic regression models. We actually won't use the more general formulation in the material that is presented here, but it has actually been shown to be useful once you go on to more complex natural language processing structured prediction tasks. Here's a quiz question for you guys to work through. So we're still in the situation that we're wanting to choose some class for the final word, which is now Guric, and our choice of classes are the same classes as before: person, location, or drug. And we have exactly the same three features that we've been using throughout these examples. And so what we'd like you to do is just concretely work through what the probabilities that are assigned to each of the three classes this time. Okay, now I hope you understand the math of a Maxent model and the sense in which it's one of the family of linear classifiers.